All right. Thank you for coming. Happy Thursday. If you've got homework 2 and I haven't gotten it yet, make sure to bring that up. I've got a pile right here. My plan for today is we need to finish chapter 1. So I might start with some of the, I think 16 and 17 on the packet just to get us going and talking to each other. And then my plan is I'll power through the rest of chapter 1 and then we'll do the packet problems to finish out with whatever time we've got left. So that way we'll finish the chapter today. And then on Tuesday, we'll have review problems. And then on Thursday, we'll have the exam. Sounds good? Thursday is also when the homework for this chapter, homework 3, will be due. So make sure you're working on that as well. It'll also give you practice for the exam. Okay, so let's start off with at least packet numbers 16 and 17. Move this over here. 16 and 17. Nope, that's not what I want. 15, 16. Um, okay, there's 2 halves, but there's 3 problems for number 16. So I'm gonna pass out markers and I'm gonna tell you A, B, or C. And then there's 3 left of these. So I don't know if maybe markers, but you do A for 17 and A, B for 17. And let's see for the C. That graph looks so cool. I love that. This is what I love about graphs, is that sometimes they just like look awesome. I'm not gonna draw it as well as you did. That's not the edge. Oh gosh. Let's try again. We've got a cycle going all the way around. Is that a vertex in the middle? Or just the edges are crossing? Crossing, okay. One, two, three, four. There's verticals too. 1, 2, 3, 4, 5. 1, 2. I think I may have gotten all of those. And for A, we've got a simplified version of that. Oh, wait, that looks cool. Got loops in there.
It's got something.
Wouldn't the loops give it 6?
Oh.
Because don't loops contribute to regularity? Because there's one going out, one going in. So that would be, wait, 1, 2, 3, 4, 5, 6. A 6 regular.
I guess so, yeah. No, I was thinking of it as just one, but yeah.
Cool. We've got one for R equals 6 where this we've got loops. Okay. Great job. That's yeah, so we've got crossing. That's for B, right? One, hold on, let me see. Cool. And then 217. Have we verified? Okay, cool. So let's review a little bit. So last time we talked about walks, paths, and trails. Walks just being a succession of edges, where we can write it as pairs of edges, or we could just smush all the vertices together and just write it like that. And then just assume when you go from one vertex to another, you take that edge or one of the edges if there's multiple. From there, we have, where's the document? All weird off on the side like this. Maybe we could not do that. I'm so confused. Okay, this is how it's gonna go. So a trail is a walk, but all the edges are different. And a path is a walk, but all the edges and all the vertices are different. So no repeated edges, no repeated vertices. And it's a scale of more to less restrictive for what we can repeat. Trail is the Bridges of Königsberg problem. Talked about connected, where a graph is connected if there's a path between each pair of vertices, every pair. Otherwise, we call it disconnected. And this one we can kind of see intuitively where this one is what we would say connected. And so is the one on the right, but the one on the right's got a bridge, which is where if we delete an edge, then the graph is disconnected. So an edge is called a bridge. If we were to remove it, then the whole graph would be disconnected. And there is an edge, so this middle edge is a bridge, even though the ones surrounding it aren't. So there could be one option for a bridge, there could be no options for a bridge. When a graph is disconnected, but still all together in a graph, we call those separate things components. So these are connected components because the triangle is one component, the vertex is one component, this path of length 1 is one component. And then we talked about what it means for it to be closed, which is where it starts and ends at the same vertex, so it loops its way back around. And so we've got a closed walk, a closed trail, but then for a closed path, we call that a cycle, where it's the edges and immediate vertices, so everything except for the start and end vertex have to be different. All right, and then we talked about regularity, where regularity, a graph being regular means that all the vertices have the same degree. So the ones that you've drawn, these graphs are regular. All of the vertices, you can count the number of edges that each of them have. And if we were to write the degree sequence for this one, it would be 3, 3, like 8 threes. They've all got the same degrees. For the other ones, like the regularity of this, if we were to write the degree sequence, it's just 4, 4, 4, 4, 4, 4, 4. Right? If we are writing down the degree sequence, all the vertices have degree 4. The term we call for that is regular. And so we say that a graph, if it's regular, we call it R regular, just to say, here's the number. So this graph is 4 regular. This graph, no, this is 1, 2, 3. 3 regular, this one is 4 regular, and this one is 5 regular. Right? We just attach the number that applies to this graph. So we had some examples. So an R regular graph or a 0 regular graph where there's just no edges, the degrees are all 0. A 1 regular graph that happens to be disconnected. A series of 2 regular graphs. Here the loops for a single vertex counts as 2 because there's one going out and one coming in. Also the case for this pair of vertices with 2 edges between it. 3 regular graphs, and I didn't feel like drawing the 4 regular graph, but we'll get to K5 in a minute, and that's a 4 regular graph. And then we ended with theorem 2.2, which states, let G be an R regular graph with n vertices. So we've been looking at like a 3 regular graph with 8 vertices. So just assigning variables to those, an R regular graph with n vertices. And then we want to prove that G has n times R over 2 edges. And the way we prove that is, so, okay, we've got a graph with n vertices. Each of them have degree R. We've got a theorem for the sum of all of the degrees of vertices. That's the handshaking lemma, where we have the sum of all the degrees is equal to 2 times the number of edges. Right? That's the handshaking thing, where if everyone in this room shakes hands with each other, we'll have, if each person counts how many handshakes they did, there will be 2 times more than actual handshakes that occurred. So we use that lemma. So we add up all the degrees, which are just R, and there's n of those, and so that's n times R. And so then by the handshaking lemma, we can get n times R equals 2 times the number of edges. Just divide both sides by 2, and we get nr over 2 equals the number of edges. So then the trick for problem 17, or what it's asking you to do, is to just verify that. So we just want to show that n times r over 2 is equal to the number of edges. So first ask, what's n? Then what's r? And then how many edges are there? And then ask, is that n times r over 2? So let's look at the first one. How many vertices do we have? 5. So n is 5. What's r? What degree does each vertex have? 2, right? Each vertex has degree 2. So, and how many edges do we have? 5. 1, 2, 3, 4, 5. Okay, so 5 times 2 is 10, over 2 is 5. 5 times 2 over 2, that's 5. The theorem holds. So we've seen that NR over 2 is equal to the number of edges for A. So A is good. What about B? How many vertices do we have? 5, 6, 7, 8, 9, 10. So 10, and then what's the regularity? 3. That's going to be 5 times 3, which is 15. And so does this hold? Do we have that many edges? 5. Another 5 here for the little guys, and then 5 for the star. So yeah, we get 15. And then C is just, it's giving you steadily more complex graphs just to have you prove that this theorem is right. So I'll let you do that one on your own, just to prove to yourself. Okay, problem 18 we'll maybe get to at the end if we've got time. But I would like to talk about would you let me draw, please? I would like to draw. Special regular graphs. So we've talked about regularity. There are some special ones that you should probably know about. One of which is complete graphs. Complete graphs are where each vertex is going to be joined to each of the other vertices by exactly one edge. So this bit, the exactly one bit, that's important because we're assuming that we're in simple graph land. With just means no loops, no multiple edges. So each vertex is going to be joined to each of the other vertices. That's a complete graph. And the way we express that is the complete graph on n vertices is written capital K and then subscript n. So n is the number of vertices, and K means complete. Probably, I don't know, I usually blame German for this. Okay. Complete graph, every vertex is adjacent to every other vertex. So let's look at some examples. K1, just a vertex. No edges to be joined because there's no other vertices. K2 is just a path of length 1. There's 2 vertices and they're joined by an edge. K3 looks like a triangle, where this one's joined to all the other possible ones, and that's the same for everyone as we go. K4, we start off as a square, and then we cross those. K5, this is our 4 regular graph. Where we've got the cycle around the edge, but then we've got the star in the middle, where each one of these vertices is adjacent to every other possible vertex. And this can go on. We could draw K6, K7, but that's a lot. I think you get the idea. If K5 is regular, are the rest of them regular? Looks like it. In fact, they are. We can use our theorem where it says n times r over 2. So we know n, we're given n. What's r for a complete graph on n vertices? So first of all, this is 4 regular. What's K4? What's r for K4? 3. 1, 2, 3. What's r for K3? 2. R for K2? 1. R for K1? 0. So what do you notice about the relationship of n and r? Yeah.
R is n-1.
Yeah, which makes sense because every vertex is adjacent to every other vertex. And so each vertex, because there's no self loops, it's going to be adjacent to, there's n minus 1 other vertices available. So it's going to have all of those edges. So using our theorem, we can say the degree of each, the degree is n minus 1. And the number of edges is going to be n times, then we plug in r, n minus 1 over 2. And that's just using our theorem. Once we've proved the theorem, now we can use that equation. So now if we ever want to, we know how many edges a complete graph has. That's a special kind of regular graph. Another kind of regular graph is a null graph, which honestly I have never seen because it's fairly uninteresting. A null graph is just a graph with no edges, so just vertices. We write it with capital N, and then the subscript is the number of vertices. And so this is just degree 0. So like this is N3, the 3 vertices, no edges. Not very interesting. So that's a null graph. So where there's complete graphs, there's null graphs. There's also cycle graphs, which is just, the graph is just a single cycle. Of vertices and edges. You might guess we write it like CN. C stands for cycle. And so like C1 could be a vertex with a self loop. C2. You typically don't see C1 and C2 because we tend to assume simple graphs. But if you do see C1 and C2, they would be non-simple graphs. C3 is the same as K3, which is just the triangle. C4 is almost like K4, but without the edges in the middle. So just going around the square. C5 is 1, 2, 3, 4, 5. You get the point. We just add a vertex and draw that cycle. Okay. That's packet 19, which we will get to as we go on. The other kind of regular graph, regular. So what's the regularity of a cycle graph? What's the regularity of each one of these guys? 2, right? Because each vertex just goes left and right. Those are my buddies, so regularity is 2. The textbook also mentions Platonic graphs, which I will show you. Oh, I wonder, did I bring it in my backpack? I did. Okay. You pass it around to like, if you know like D&D dice, the Platonic solids are like there's a tetrahedron, which is a D4, octahedron, which is a D8, dodecahedron, which is a D12, 12 sides, hexahedron, which is just a cube, which is just like your standard dice, and the icosahedron, that's the D20 with 20 sides. And so these are the Platonic solids, and what we can do, here, let's take this one. Copy image. No, it's putting it at the top. Okay. Where did it go? It went here. That's okay. So the idea is we take all of these and we say, let's make each point here a vertex and each edge here an edge, and just make it into a graph and smush it down into the plane. So from there we get the tetrahedron, which is like if we took the top of it and just flattened it. The cube, we have to like bring out the bottom part, stretch it out a little bit, and then we can smush it down. So for the cube, we get something like that. And so on. I'll leave the drawings to the book. I think they look pretty cool. These are also incidentally called, they also belong to a category called polyhedral graphs, which is generally if we take a convex polygon, so something that doesn't have like any concavity part, so no like what's like if you didn't like punch one of the edges in to create some concave area, then you've got a convex polygon and you can draw it as a graph like this. This is something that I looked at for my dissertation thesis. So when I saw this in the textbook, I'm like, I know about that. So yeah, so these are Platonic graphs because these are Platonic solids. I think in particular, the icosahedron and the dodecahedron, those look pretty cool. But yeah. There's also a really famous regular graph called the Peterson graph. This is a 3 regular where with 10 vertices and 15 edges, where I'll draw this one. And then we have an edge to the outside, and then a cycle all the way around. And in the book, there's another formulation of this, which I think looks quite cool. The Peterson graph is used for counterexamples a lot, which this is something I also looked at in my dissertation. Just what it's really useful if you are trying to prove something because it's regular. There's an even number of vertices. This graph has what we call odd cycles. Odd cycle meaning the number of edges in this cycle is odd. So like K3, the triangle, that's an odd cycle. Awesome, thanks. But C4, the square, that's an even cycle because there's 1, 2, 3, 4 edges, which is even. So the Peterson graph doesn't have any K3, but it has 1, 2, 3. Now that I'm gonna try and find one, I'm not gonna be able to. But it has odd cycles. And so that leads us into our next topic, which is bipartite. So this is a definition. There's probably going to be a whole chapter on bipartite. So a bipartite graph is a graph whose set of vertices can be split into 2 subsets. And we typically call them A and B or X and Y or some capital letter to denote that these are 2 sets of vertices. So we can split them into 2 subsets such that sometimes you'll see ST for such that, that's just an abbreviation, such that each edge of G, let's name this G up here, each edge of the graph joins a vertex in A with a vertex in B. So all of the edges go only between A and B. There are no edges inside of A. So you'll typically see something like Let's use pretty colors. We say this is A, and then let's make it purple. And this is B. All of the edges in the graph are going to go from A to B, or like between A and B, and not inside A and B at all. So this is a bipartite graph. Because it's bipartite, sometimes you'll see we can draw it with colors or simpler, just two colors like black and white. So the cube graph that we saw before, that's a bipartite graph, and we can prove it by drawing the graph with either like a filled in circle or an open circle. So that's like the inner part, right? So C4 is bipartite because we can draw one vertex with the open circle and the other vertex with the closed circle. And they alternate, right? So if one vertex is open, the other is closed, then the next one has to be open, and so on and so forth. So because we can draw this in a way where we only connect the closed to the open and the open only to the closed, you can say that this graph is bipartite. So I'll say no edge within A or within B. If there's an edge like here, then this makes the graph not bipartite. Okay. Are we good to look at an example? Okay. So problem 20 is prove that every cycle has an even number of edges. That's a property that belongs to bipartite graphs. So I don't think this one that I drew here, if this dashed edge doesn't exist, there's no cycles in this graph. If there were cycles, the cycles would only be even. There's only an even number of edges if cycles were to appear in this graph. There's no cycles here, so it doesn't apply. But we've seen a bipartite graph before. That's the three utilities problem, right? Where something like that. There's cycles in here, and so if you try and follow them and get back to the same one as quickly as possible. So let's say we do that. That's still 4, and so that's an even cycle. So no odd cycles are possible. This ends up being a complete bipartite graph. Where we can combine these definitions of we know what bipartite means and we know what complete is, and so we modify the complete definition to apply so that the bipartite property still holds, where we've got these two independent sets, which is just that every possible edges is there while still maintaining the bipartite property. So every possible edge is included. While preserving, let's spell preserving right. Preserving the bipartite property. Property. So for this one, we've got 3 vertices in one, 3 vertices in the other. So if this is A and this is B, every vertex in A is adjacent to every vertex in B. And vice versa. Every vertex in B is adjacent to every vertex in A. But since the graph still has to be bipartite, we can't draw the edges connecting A to A, B to B. The way we write, so we write a complete graph just with how many vertices there are. The way we write a bipartite graph as complete is we still use the letter K, but we instead have 2 letters. So if the size of A is N and the size of B is M, we write it KN, comma M, where these are both in the subscript. The book uses KR, comma S, which are just different variable names, so that doesn't really matter. The thing that matters is that we've got 2 variable names here, X, comma Y, instead of just 1 for N. All right. All right, we're almost there. We're gonna make it. We've got until, I always forget. We've got until 20, so we're good. Another kind of bipartite graph is a tree, which a tree is just a connected graph with no cycles. And so with no cycles, that bit we can call a cyclic, A meaning no, and cyclic meaning cycles. So it's a connected acyclic graph. So that chemistry one that we've seen before, I think it's ethanol, where we can draw it like this. That's a tree. It's connected, there's no cycles. Great. There's another one. We could, I don't know, just draw something. This one kind of maybe looks like a dog with 3 heads, I guess. Maybe it's a Cerberus. It's a tree. It's a graph with no cycles. If you typically if you like break an edge, but you can still consider this like a whole graph, we could call that a forest, because computer science likes naming things. So if there's not one tree, then there's multiple trees, which makes it a forest. Let's see. And this is kind of where we also get the idea of, or it is where we get the idea of, from here we can put restriction on this, like a binary tree, which is where maybe if we have a root, which is somewhere where we start, say this is the start of the tree, and then we enforce some decision where each node only has 2 neighbors, then we get what's called a binary tree. And so typically we draw it like this, but since it's a graph, we could also draw it like this, doesn't matter. We're just enforcing some notion of direction onto it. So we can have a binary tree, we can have a binary search tree, where if each of the nodes is associated with some data point, then we have some property that we want to enforce upon when we add the data in, then we've got a binary search tree. Or we could have like a decision tree for something like machine learning, where if each node we have a decision to make and say if something holds, go left, if something else holds, go right. Or maybe we have, it's not a binary tree and there's multiple options. So a tree is kind of the foundational property for some really interesting machine learning and algorithmic things that we can do. And they're bipartite. We could draw each of these, like let's say, I'll use the highlighter. So if we color this with 2 colors, this gets no color, the neighbors gets 1 color, those neighbors don't get colored. So we can color this with 2 colors, therefore it's bipartite. An interesting theorem we can have, which I don't believe the book labels, so let's maybe call it a lemma, is the statement is, I'll write this, and this means there exists exactly 1. So it's the sort of backwards E, that part's this there exists, and then the little exclamation point means exactly 1. So the statement of the lemma is there exists exactly 1 path between each pair of vertices in any tree T. So in any tree, for any pair of vertices that are in there, any ones, there is only going to be 1 path between them. Which kind of makes intuitive sense, right? Like if you look at this one, like if we choose this one and this one, obviously there's only 1 possible path. And so the intuitive proof is that because there's no cycles imply there's 2 ways to get somewhere. But since there's no cycles, then there's only 1 way to get there. So yeah, so if we wanted to prove it a little bit more rigorously by contradiction, so we assume that the tree T is connected, which implies that we know the connected definition is there's at least 1 path between any pair of vertices. So there exists at least 1 path between any pair of vertices. So let's do contradiction. And so let's suppose that there's a pair somewhere in this graph that's joined by 2 paths. So suppose there's a pair joined by 2 paths. That implies that there's a cycle. So because we assume a tree is acyclic, now we've reached a contradiction. Therefore, we can write, so there is only 1 path between any pair of vertices. So, and this only holds for trees, right? If it's if the graph is cyclic, if there are cycles in there, so these ones that you've drawn, it doesn't hold because there are more than one path between any pair. Okay, that's trees. The other one I want to mention are path graphs. These are not regular, but are bipartite, which we just write P, capital P with the subscript N to say that like this is P of one. This is P of two, N being how many vertices are in this path. It's P of three vertices, just the path between them. These are bipartite. They're not regular because like take P3. The middle one has degree 2, while the two edges have degree 1. So it's not regular, but it is bipartite because we can go through, if we color the first one, then we don't color the second one, and we color the third. And we didn't reach any conundrum. Let's take for a second an odd cycle and see what would happen if we colored that. So if we do this one and then we go clockwise, so we colored the first one and then we can't color the second one. And then we get the third, not the fourth, and the fifth. But this is where there's a problem because we've got two of the same color adjacent to each other. So we say that this graph is not bipartite. And that's the reason why. Okay. How many edges does a path graph have? Yeah. N minus one edges? Yeah. Because we know that like a cycle graph is gonna have n edges. Like C5 has 5 edges. So a path and then a path graph is just we delete the edge like going from one to the other. So if a cycle graph has n edges, then path graph has n minus one edges. Okay, so I think that's all I want to talk about for this chapter. The book also, after this, they have a case on cubes for like coding theory. If that's something of interest to you, I encourage you to look at it. They also have 2 case studies, one of which is, I forget, there's like a color, they have like cubes that form a game and use graphs to try and figure out the solution. And the other is looking at signed graphs. So I think we don't need to cover those for our definitions. If you would like to, then feel free. But in any case, I think we're done with this chapter. So for the rest of the class, I'll, let's see, where did we start or stop? I figure we go through the packet and that's our practice. So we stopped at problem 18. So if, let's say this half of the classroom wants to prove A and this half wants to prove B, and you can talk to each other and then write one up on the board and then we'll talk about it. 7.73, 21/2, and then half edges. Does it make sense to have a graph with half of an edge? I don't know what that looks like. So that's our contradiction. So there are no 3 regular graphs with 7 vertices. Excellent. Yeah, that's great. So that's for a specific example. What about for the general example? So it's going to be the same kind of structure, right? Where'd my pen go? There it is. So you come to a contradiction where we know n times r over 2, and we plug it in, so it's 7 times 3 over 2, and this is 21 over 2, which is 10.5. And the key factor here is that 21 is odd. And so if we're trying to prove the general case, where we're looking at nr over 2, which is the similar way that we're going to get this answer, we have to look at the parity. Parity meaning even or odd. We have to look at the parity of both of these numbers. So, because we want n times r to be divisible by 2. That's what makes this work out. So let's look at 3 cases. Let's look at one where n is even. So if we have an even number, first of all, if we have an even number times an even number, that's going to be even, right? Because we'll get 4xy, which is divisible by 2. So if they're both even, great. If one of them is odd, so let's say 2x times 2y plus 1, then what? We get 4xy plus 2x, which we can factor a 2 out of that. So if this is where we can say without loss of generality, because if we have 2 times 4 or 2 times 5, 2 times 5 is equal to 5 times 2, right? So case 2 is where only one of them is odd. Let's spell odd. So without loss of generality, I assumed the second one was odd, but since we can switch multiplicative terms, that's fine. So this is, neither of them are odd. The third case is that both are odd, which is where we've got 2x plus 1 and 2y plus 1, where if we FOIL that out, we get first is 4xy, outer is 2x, inner is 2y, and then 1 at the end of that, which I hope you can see is odd. So we can factor a 2 out of those first 3 terms, and then we get a plus 1 at the end. So both odd means that those 2 things multiplied together is odd. And so this is where we get our contradiction. So when we assume that n and r are both odd, which is our assumption here, then the numerator cannot be, the numerator will be odd, which gives us an impossible number of edges. So that's where we get the contradiction. So the numerator means that it's odd, and that's our contradiction, because we can't because then this fraction isn't an integer. And the fraction, or the fraction as a whole needs to be an integer because that's how we represent the number of edges in a regular graph. Questions on that? Or need me to go through it again? Okay. We've got 3 minutes, so this, I know what N7 is. It's extremely boring. 1, 2, 3, 4, 5, 6, 7. Great, we did that. C7. You just go all the way around, right? It's a cycle. C for cycle. 1, 2, 3, 4, 5, 6, 7. Great. K7. That's the complete graph on 7 vertices. So for every vertex, we're just drawing all those possible edges. Okay, I think I got all of them. It's going to be messy up here, but I think you get the idea. Okay, so it's 11:19. So we'll stop here for the day. Make sure I get your homework too. And then on Tuesday, we'll use the rest of the packet as practice and other things for the exam. And then Tuesday we'll have homework due and the exam. Thanks for coming. I'll see you on Tuesday.